Hello friends, Mr. M here. Welcome back to another exciting mathematics lesson. This is AS level. We are still continuing with advanced subsidiary mathematics. Right, today we want to do we want to look at integration, and today is going to be an intro course. It's one of those really important courses. We're just going to set the foundation and just to make us able to continue with this chapter. I've just finished doing a series on differential calculus. Now, integration and differential calculus are twins, if you like. I don't like saying they're opposites, but anyway, we can say that they are reverse functions. Okay, it's just like multiplication and division. It's just like addition and subtraction. Okay, it's just like factorization and foiling or multiplication again. Okay, so you cannot do one without the other. It's very important if you've missed anything on differentiation, or if you find yourself overwhelmed with integration, especially when we do graphs, when we look at areas under the graphs, when we look at the curves, maxima and minima problems, please go back to the differentiation series that I've just done and just refresh your mind on there. Right, so for today, we want to look at the introduction to integration. As I've mentioned, integration is the opposite of differentiation. Let me prove that to you. Let's suppose you are given a function y is equals to, totally making this up by the way, 3x squared plus 2x plus 1, and you are asked to find the derivative of this function. Find the derivative of y with respect to x. So according to our integration rules, you know what to do from here. Let's do it. So dy dx, this is a sum, and we know the rules of integral. One of the rules says that the sum of the derivative is the derivative of the sum. So we will take the derivative of each term in turn and then sum them up, and that's going to be our solution. The derivative of 3x squared becomes 6x. The derivative of 2x becomes a 2, and the derivative of 1 becomes a 0. And this is our solution. But now let's suppose we were given this to start with, and they want us to find the function that was derived to arrive at this point here, to get this gradient here. So we want to find the original function that was derived to get that gradient. Now for this particular task, we will have to integrate it. We'll have to apply our integration rules. So we are given dy dx is equals to 6x plus 2, and we want to get back the original function. This is going to be a little bit tricky in the end, especially with the constant, but I'll explain as we go on. Right, so what we do here, the rules are that to get this function back, you add 1 to the power, divide by the power, add 1 to the power, divide by the power, add 1 to the power, divide by the power, add 1 to the power, divide by the power, add 1 to the power. You get the picture. Add 1 to the power and you divide by the power. We have 6x squared. The power is 1 there, so y is equals to 6x to the power 2. You add 1 to the power, so it's 1 plus 1, 6x to the power 2, and you divide by the same power, or by the new power, which is 2. Add 1 to the power, divide by the power, plus. Now remember that if you have a constant on its own, it's really not on its own. You can assign a variable to that constant depending on what you are differentiating with respect to, but that variable has to be to the power 0 such that it balances mathematically. Anything raised to the power 0 is equals to 1. So you haven't changed anything, you haven't cheated anything. So if you imagine that you have 2x to the power 0, add 1 to the power, divide by the power. So you've got 2x to the power 0 plus 1 divided by the new power, which is 0 plus 1, which is 1. Now, when we get to this point, it's very easy to ignore the fact that there's nothing there and you leave it there. And that's where the problem starts. Remember that when we are differentiating a constant, we get a 0. So we have to assume that there was a constant that was differentiated somehow to get a 0. Even if there wasn't, 0 is still a constant. So we have to represent the derivative of that constant. Okay, so we have to assume that there was a constant that was differentiated, which was c, that gave us a 0, hence we didn't have anything there. This is very important later on, because at this point you will just realize that all of this function here that we've just obtained is called the general solution. And the reason why is because of this constant here, this arbitrary value here, this arbitrary value, arbitrary value of c. This whole value here represents all the y values that the graph intercepts as it is swooping through a two-dimensional plane. Okay, so we don't know what it is. We cannot get it from here. We need extra information. The best thing that we can have is to know what point the curve passes through. Then we can map out its path, or we can find its trajectory and know how it was translated, so that we can find a specific solution. At this point, we are happy with just solving this. Okay, 6x squared divided by 2, that becomes 3x squared. Check, which is that term there, we've got it back, plus 2x to the power 0 plus 1, that just becomes 2x to the power 1 divided by 1. Check, we've got that term there, plus that arbitrary value c, plus c there. Check, we've got that constant 1. Okay, right. At this point, I want you to be happy with just that c being a constant 1. If we are given extra information, we can find that 1. Next question, or we can find that constant, sorry. Right, and that is how we do that. The following question now, or a sub question to this, follow-up question to this. Suppose now you are told that this curve passes through a certain point. Okay, this curve passes through 1 and 5. Find the specific solution, not the general solution now. They want us to find the true solution, the specific solution, meaning they want us to find that value of c which the curve will intercept. In this case, because we are given an ordinate and an abscissa, this is gold information. This is really, really good for us. So what we do, we substitute that 1 and 5 into the equation that we've just obtained there to solve for c, and then once we've solved for that, we'll back substitute that c, and we'll have a specific solution or specific equation that we can sketch. So let's do that. Y is equals to 5 and x is equals to 1. So I'm going to substitute 5 there is equals to 3 times 1 squared plus 2 times 1 plus c. Let's do some quick footwork here. 3 times 1 is 3 plus 2 times 1 is 2. So our c is going to be equals to 0. Therefore, c is equals to 0. So that equation, y is equals to 3x squared plus 2x plus whatever value of c you find here. In this case, it's just 0. We can just leave it as is. If it was 1, we would have substituted 1, whatever the value of c was going to be. So now this is not an arbitrary solution anymore, but this is a specific solution of a particular function in terms of y. Thank you very much, folks. I hope you enjoyed watching that. Look forward to other examples in this exercise, but please keep practicing exercise 6a on page 177. Have a good day, keep well, and keep safe.